Hi, our topic for today is about integration of exponential functions. At the end of this lesson, you should be able to apply the two basic formulas for integration of exponential functions. There are two basic formulas for integration of exponential functions. The first is the integral of e to the u du equals e to the u plus the constant c. The second is the integral of a to the u du equals a to the u over the natural log of a plus the constant c, provided that a is greater than 0 and a is not equal to 1. So let's take an example. Suppose we are asked to evaluate the integral of y raised to y squared plus 4 dy. So we let u be the exponent of e, which is y squared plus 4, and then we take the differentials of both sides, so du is 2y dy. But if you look at the integrand, there is a missing constant of 2, but y dy is part of the integrand. So to remove 2 and to solve for y dy, you divide both sides of this equation by 2 to get y dy is du over 2. Then by substitution, we can now replace y squared plus 4 by u, and then this y dy by 1 half du. And because 1 half is constant, so you can factor this out. So you have the integral of e to the u du. But recall that the formula for the integral of exponential function of this form, e to the u du, is e to the u plus the constant c. And because there is a constant coefficient of 1 half, so you multiply this to e to the u. But we know that since the integrand is in terms of y variable, so your final answer should be in terms of y. We have to replace u by y squared plus 4. So we have 1 half e to the y squared plus 4 plus the constant c. So let's take another example. Again, we are asked to evaluate the integral of e to the tangent x dx over cosine squared x. So for this problem, we will apply the integrals of exponential function, wherein the integral of e to the u du is e to the u plus the constant c. So for this type of integrand, we let u be the exponent of e, which is tangent x, and then taking the differentials of both sides, so du is secant squared x dx. So we can replace tangent x by u, but there's no secant squared x dx in the integrand. But we know that there is a relationship between secant and cosine. Recall that cosine is 1 over secant, or secant x is 1 over cosine x. So therefore, we can rewrite 1 over cosine squared x as secant squared x. So we have the integral of e raised to tangent x secant squared x dx, and then by substitution, this can be written as the integral of e to the u, where u is tangent x, and then secant squared x dx is du. But recall that the integral of e to the u du is e to the u plus the constant c, where u is tangent x. So the final answer is e to the tangent x plus the constant c. Okay, suppose we are asked to evaluate the integral of quantity e to the x plus 1 quantity raised to the second power dx over e to the x. So to integrate this, we need to expand e to the x plus 1 squared. So the expansion is e to the 2x plus 2e to the x plus 1 divided by e to the x dx. And then we divide each of the term of the numerator by e to the x. So we have e to the 2x over e to the x dx plus 2 times the integral of e to the x dx all over e to the x plus the integral of dx over e to the x. And then we simplify each of the term. So we get e to the 2x over e to the x is e to the x. We apply power formula plus 2 times e to the x over e to the x. You cancel this out. So we have dx plus the integral of dx over e to the x. But If we place this in the numerator, we get e to the negative x dx. So the first term is of the form, recall the integral of the formula, yung e to the u du is equal to e to the u plus the constant c. So because this is similar to this formula, the integral is e to the x plus 2 times the integral of dx, which is x minus the integral of e to the negative x dx. Again, this integrand is of this form, wherein we let u be as negative x and the differential as negative dx. Then we solve for dx. You multiply both sides of this equation by negative 1. So we get negative du is positive dx. So therefore, e raised to negative x dx can now be written as e to the u, or integral of e to the u times dx, but dx is negative du. Then you factor out the negative sign, so we have e to the u du, where the integral of e to the u is e to the u plus the constant of integration. But since we know that u is negative x, so this should be negative e raised to negative x plus the constant c. So therefore, the final answer is e to the x plus 2x minus e to the negative x from here plus the constant c. Okay, next example, number 4. Again, suppose we are asked to evaluate the integral of 5 raised to x plus 2 dx. Okay, recall that the integral of a to the u du is equal to a to the u over the natural log of a plus the constant c. So for this example, we let u be the exponent, which is x plus 2. Then we take the differentials of both sides, so du equals dx. And then by substitution, this can be written, you have the integral of 5 raised to x plus 2 dx equals the integral of 5 raised to u, where u is x plus 2, times dx, but your dx is du. So using this formula, your base is a is 5. So this should be 5 raised to u over the natural log of a, where a is 5, plus the constant c. But because u in terms of x variable is x plus 2, so this can now be written as 5 raised to u, where u is x plus 2, all over the natural log of 5 plus the constant c. So in summary, after evaluating integrals of exponential functions, we have learned that proper identification of u and du must be performed first before applying the integration of exponential functions formulas.